So what are the factors that affect TG, the structural factors? The most important is mobility. It's not much different than the inorganic classes. Remember, higher mobility by adding things that break up the network of silicates lowers the TG. Same with polymers. So mer mobility affects TG. So the most important one is polybutadiene. Polybutadiene, so it is from the 1,3, so it's 1,3-butadiene. So what is that? Well, it's got bute, so it's got 4 carbons, and it's 1,3-diene. So if this is carbon 1, there has to be a double bond at carbon 1, carbon 2, carbon 3, carbon 4, and there has to be one at carbon 3. So then you can put all the necessary hydrogens on. Now what happens here, if this is 1, 2, 3, 4, what happens when you polymerize this is that you form a radical here, that, so you get some initiator, the radical attacks this double bond, it moves the radical here and here, and forms a double bond in here and leaves a radical at this end. So what happens is that what was carbon 1, where you had a double bond between carbon 1 and 2, you now end up with a double bond between carbon 3 and, or carbon 2 and 3. And that's H2, H, H, H2, and this repeats. And this is in your reading if I went too fast there. But this is polybutadiene, and you can see this material is restricted turning here, but it's easy to bend, can rotate at these carbon-carbon single bonds. And in fact, this is a naturally occurring material. It's found in the rubber tree. It comes out as a latex. It's a white milky substance. It's used by the tree to protect wounds. So as the latex oozes out onto the bark, it dries and cures and makes a rubber cement seal. I'm not kidding. And it's a latex, it's little droplets of this oil-like substance, this polymer-like substance. That's what a latex is, little tiny droplets. And this material, of course, has a very low TG because it's highly mobile. TG is around minus 90 degrees C. In fact, this was known as a gum. The original use of this material was a gum. Now you'll notice there's sort of a cis-trans opportunity here, right? So I could have this carbon bond on the same side as this carbon bond, or it can be on the opposite way that I've shown it here. So there's cis-trans opportunity. And so the properties will vary depending on how much cis and trans is in the gum, but generally it's pretty random. Compare that with our favorite polystyrene. Polystyrene, TG is 90 degrees C. Now why do you think there's such a big difference between this and the polystyrene? Well, the substituent on the polystyrene, remember, the thing that's every other is a benzene ring. A group that's... So how flexible do you think this MER is? If I'm going to bend this thing, I have to bend this big group through a long distance. And so the TG, when it goes, as soon as you start adding stuff like that, you go from minus 90 up to 90 degrees C. So, that's out of order, sorry. Where is it? This is what I wanted to show. So this is a modulus curve. Young's modulus. Remember Young's modulus. That's the slope on a stress-strain curve. So let's do that. So here's my stress, here's my strain. And let's just draw what we think polystyrene looks like. Well, polystyrene's a glass. No plasticity. Goes right up. And of course, up until it breaks. Maximum fracture stress. What do we think this gum does? Well, what the gum does is it kind of does this. And then, like that. This is called an elastomer. We're above the TG. And so the first thing you notice is that the slope here is a lot less than that. And the slope is the modulus. Right. Now what's happening here is I can, as I'm down here, I can, as I pull, I can rearrange these polymer molecules. They're mobile. But at some point they're straight. And they're so entangled you can no longer move them. And so it just takes off. And of course, that will fail too, like the rubber band does.
Sorry, so what was the first curve that goes straight up?
This is below the TG. Thank you, I should have written that. And then this is above the TG. So the properties completely change through the TG.